Welcome back everyone. In the previous tutorial we saw how to test and evaluate the functional simulation of our accelerator. Now the last step is to take this accelerator and to physically put it on an FPGA. Opening the script again, let's remove the part about the functional simulation. And we can call again write VHDL in order to generate again the files which will contain the VHDL description of the accelerator. Let's use the rm equal to true as a flag in order to remove the previous version of the accelerator and to regenerate it. Now we need to specify the functional flag equal to false in order to generate something that is synthesizable, and to generate also the interface in order to guarantee that all the signals of the accelerator fits within the available number of pins on the board. I will show you in a while the specific board to which I'm referring. If we now run the code, Spiker Plus will generate the VHDL description as we saw in the first tutorials. We can now start the Vivado graphical interface, which is the easiest way to configure and interact with the project and with the hardware that will be put on the FPGA. We can create a new project, and as a name for the project we will use a Spiker in order to identify our accelerator. It will be put on the working directory, that is the desktop in this case, and then we can select all the VHDL files that were generated by Spiker Plus. So we can go into the output directory and select all the files. Basically all of them are needed in order to create the architecture. After this step, Vivado will ask for a constraint file. This is a file that contains the physical mapping between the pins of our architecture and the physical pins of the board that we are targeting. In this example we will target a pink Z2 board. So first of all we can go to the vendor website, that in this particular case is TUL, T-U-L. And going on the website of the vendor you will find a section containing all the files relative to this board, and in particular the master XDC is the file we are searching for, which contains a template for specifying the constraint to map the pins from the architecture to the physical pins of the Z2 board. Now if we open the zip file that was downloaded, you can see the XDC file is the file containing this template mapping. You can see it is simply a text file which contains some definitions, like the definition of a clock, associating it to a particular pin, and connecting it to the sysclock signal in this case. We will change the name with our clock. And then for all the pins available on the board, like the switches, the LEDs, and all the possible I/O ports, it maps the name of the pin to the name of the internal pin in the architecture. So let's now include this constraint file in our project. And then we need to specify the board on which we want to work. So let's use the board tab to select the pink Z2, and we can complete the creation of the project, and Vivado will set up all the environment to work with the pink Z2. After the project is initialized, you will see a full accelerator element appearing, identifying your top entity, that is the full accelerator. If we now explore all the components which is contained within the accelerator, we can go and look within the ROM component. As we saw in the previous tutorial, the ROM IP component is not generated, and this is the step in which we can include it in the project using Vivado functionalities in order to simplify the instantiation of this component. In particular, as we said, since generally the amount of weights that we need to store is large, we will use a block RAM to store all the weights. So we will map our ROM to multiple elements of this block RAM, that is in practice a static RAM, which can host larger amount of bits. We need to name the components in the same way as we named the IP components, so in this particular case ROM 40.128 xleaf1 IP, and then we will select that this component is a single port ROM, since we don't want to modify it, it is a read-only memory containing the weights. And then we can specify the width of the word that we want to read from this ROM. Now, in order to understand the correct amount of bits, let's look at the number of bits that we assigned to the weights. If you remember, in our bitwidth_config dictionary we selected 6 bits for the weights. Now, let's compute 6 bits multiplied by 128 neurons, which are the amount of neurons that need to receive these weights in parallel. So we need 768 bits for this word. And then the depth identifies how many of these words we will need, and this corresponds to the number of inputs that we expect to receive, so in this case 40. Now, we don't want to use an enable pin, we want our ROM to be always enabled, and we don't want an output register, so we want the ROM to answer in one single clock cycle. Now we can load an init file in order to initialize the ROM with the values of the weight, and this is where the COE file that was generated by Spiker Plus comes in handy. So here we see a recap of our memory, so it's a single port ROM and the amount of block RAMs that were instantiated to host this ROM, in particular in this case they are 11. And informations about the speed of the ROM and the address size. If we generate the component, you can now select the do not launch to avoid running the synthesis. We will run the synthesis at the end of all this process, and you will need to repeat this step for all the ROM memories present in the architecture. Once you repeated this step, we can generate the bitstream. This will run all the steps that are required to generate the accelerator that will be hosted on the FPGA, so the synthesis, the implementation, and then the generation of the binary file that we can copy on the FPGA. While the generation of this bitstream, so this binary file, is running, let me show you a little bit more in detail how to configure the constraint file in order to map your signals to the input-output pins of the board. So you see that you need to uncomment the lines that you need in order to connect the pins, and in particular, in this case, we are connected our clock signal to the package pin number H16, and we are connecting the spike to the switches in order to be able to stimulate the accelerator manually to send spikes through the switches. And we are connecting the output signals, so the ready signal that signals that the accelerator completed a processing step, the sample ready and the out spikes to LEDs in order to visualize this output. Then all the control signals like reset, start and sample are mapped to buttons, and the input spike address and output spike address are mapped on PMOD ports in order to send these values and to select the spikes, input spikes one by one and the output spikes one by one. So this is the way in which you map internal signals to I/O signals on the board, and this allows you to map the architecture on a physical board. Now, while the synthesis is running, you can check the reports about the synthesis. And finally, when the bitstream was generated, you can open the implemented design in order to visualize information of what was generated by Vivado. First of all, we can have a look at a graphical representation of how the lookup tables were mapped on the FPGA. You can see that even if the FPGA that is hosted on the pink board is small, the amount of memory the amount of area that is required is limited. And then you can check the timing constraints, so you see that we have no warnings, so basically the timing is respected, the accelerator can run correctly on this FPGA, and you can have a look at the power consumption of the accelerator. In this case, the estimation is of 300 milliwatts. This is a rough estimation, because if we want to have a more precise estimation, we need to run something like a post-synthesis simulation in order to measure the effective switching activity of the accelerator and to estimate the power in a more precise way. In fact, if you look at the confidence level value, it is slow, identifying that it is a first estimate given by the implementation results only. This was the last videos of this series of tutorial about Spiker Plus. If you arrived up to here, my congratulations, and I hope this series of video will help you in configuring, tuning and deploying your own accelerator for spiking neural networks.